Okay, welcome back, everybody. So, continuing with our workshop on open problems in algebraic combinatorics, Biddy from the University of Regina is going to be talking to us about the intersection density of transitive groups. And this is joint work with Karen and Pablo Spiga. So take it away, Biddy.
Okay, thanks, Nathan. So, first of all, I'd like to thank the organizers for giving me the opportunity to present my work in this workshop. So, I'm going to talk about the intersection density of transitive groups, and this is a joint work with Karen Marr, my supervisor, and Pablo Spiga. Okay, so first of all, let's recall the Erdős-Ko-Rado theorem. I think we saw it just earlier in Ferdinand's talk and in Karen's talk as well. So basically what we have is that if F is an intersecting family of K subsets of this set N, then the size of F is at most N minus 1, choose K minus 1. And when we restrict N to be larger than 2K plus 1, then the intersecting family that attain this bound are exactly the stars that we saw earlier, also canonically intersecting family. So this theorem can be extended to permutation groups, and this is how we do it. So two permutations are intersecting if they agree on some elements I of the set N, and a set of permutation in the symmetric group is called intersecting if any two permutations there intersect. So Deza and Frankel proved in 1977 that if you have an intersecting family of the symmetric group, then the size of F is at most n minus 1 factorial. And notice here that this corresponds to the size of a point stabilizer in the symmetric group. And Cameron and Larose and Malvenuto in 2004 proved that the intersecting families that attain this bound are exactly a coset of point stabilizer of the symmetric group. So the natural question is, well, whether if we can extend the previous theorem for subgroups of the symmetric group. So in other words, a permutation group of degree n. And not surprisingly, the answer is no. We already saw, I think, some examples in Karen's talk. So we can actually easily construct an example. So we take the alternating group with its natural action, and then we look at the induced action on the two subsets of the set 4. So there are 6 of these guys here. And so now we look at the isomorphic image of this group G with the induced action in Sim6. So if you look at this, this is transitive, and a point stabilizer in G tilde is going to be of size 2, but we have an intersecting family of size 4 in G tilde. So the previous theorem that I showed earlier failed to extend to subgroups of the symmetric group. So because of this, we consider some definitions. So here we let G be a transitive group acting on a set omega of size n, so the degree is equal to n. And the intersection density of an intersecting family F in G is the rational number, which is the ratio between the size of F and the size of a point stabilizer. And the intersection density of the transitive group G is the max over all the intersecting family of this row of F. So just a quick observation. So the intersection density of a transitive group is always bigger than 1, at least 1. And this is because a point stabilizer is intersecting, and when the group is transitive, um, a point stabilizer has exactly an intersection density equal to 1. And this is a definition that we already saw in Karen's talk, but here I just formulate the EKR and the strict EKR property in terms of the intersection density. So we say that G has the EKR property when rho of G is equal to 1, and G has the strict EKR property when G has the EKR property, and an intersecting family F such that rho of F is equal to 1 has to be a stabilizer of a point. So now these are some of the results in this area. So in 2015, Mars, Spiga, and Tiep proved that when G is a finite two-transitive group, then G has the EKR property. And I think Karen also talked about how two-transitive groups have the EKR module property on Monday. So the proof of this theorem uses some argument similar to the classification of the finite simple groups. I mean, it uses that in fact. And the next two theorems are asymptotic results. So in 2011, Ellis, Friedgut, and Pilpel proved that if you fix t in the natural number, so for n large, depending on t, the action of sim n on the t tuples of n has the EKR property and the strict EKR property. And in 2012, Ellis proved the analog of this for the action of sim n on the t subsets of n. So these two results are, as I said earlier, asymptotic, and the proof of these two results use the representation theory of the symmetric group and the Hoffman bound. So the first open problems that I have are the following. So basically, when n is greater or equal to 2t plus 1, the theorem of Ellis, Friedgut, and Pilpel hold for basically for this value of n and t, and this is an analog of the Ellis's proof, Ellis's theorem earlier. So for t less or equal to n, the action of the symmetric group on the t subset of n has the EKR property and the strict EKR property, except for these two values of n and t, so 4 and 2 and 5 and 2. And Karen and I proved at least the bound, not the characterization, when t is equal to 2. And when t is equal to 3, Angelo Piazzain, Roger Madeki, Aina Tukrasuamanan, and I proved that the bound holds, but we couldn't prove the characterization. And this is for just for the t set wise. So our main goal to work on this type of problem is really to classify the finite transitive groups that have the EKR property. But I think this project is very ambitious because there are some, I'll show later that there are some groups that, like with the current tools that we have now, we can't decide whether they have the EKR property or not. So now let's talk about the tools that we need to study the EKR property. So the derangement graph, and we already saw this on Monday again. So the derangement graph of a transitive group G is the Cayley graph of G with connection set equal to the set of all derangement of G, which I denote by der of G here. So the set of fixed point free permutations. And this is an example of a derangement graph for the symmetric group with its natural action. So you can see here that the identity element is adjacent to the three cycles that are, which are derangement in this case, and two transpositions are adjacent because their product is a three cycle. And this is the derangement graph of the group Alt4 of degree 6 that we saw earlier. And just notice here that this graph is a complete tripartite graph. And so why are we interested in the derangement graph? So because of the way the edges of the derangement graphs are defined, so this is what happens. So if F is an intersecting family of G, then F corresponds to a co-clique of the derangement graph and vice versa. So now the problem of finding the maximum intersecting family in a group G becomes a graph theoretical problem about the independence number. And in the talk on Monday, Karen was focusing on groups that have the EKR property. And in this talk, I'm going to talk more about the groups that do not have the EKR property. And the natural examples are groups that have derangement graphs like this. So here, this is a complete multipartite, I think, like green, blue, and red. So what we have in the green part is that, well, this is the identity. And if you notice, these are all permutations with a fixed point, and everything else here are derangements. And this is exactly what happens if we restrict our derangement graph to be a complete multipartite graph. So if we take a group element, a permutation that is a derangement in the group G, then it is adjacent to the identity. So all of these, the permutations in these parts are all derangements. And so if we take a permutation that doesn't have a fixed point, and we restrict our derangement graph to be a complete multipartite graph, then everything that has a fixed point must be in the same part as the identity. And in particular, a point stabilizer is here. And well, so if we call this part that contains the identity Fg, then in fact, what we can prove is that Fg is exactly the subgroup generated by the permutations that have at least one fixed point. And this part holds if and only if our derangement graph is a complete multipartite graph. So there is something weird that's going on here, because this implies that if I take the product of any two permutations with at least one fixed point, then the product is never a derangement. So this is like a weird property for these transitive groups whose derangement graph is a complete multipartite graph. So this is exactly what we did with Karen and Pablo. So we looked at the library of transitive groups in GAP, Sage, and I think Pablo was using Magma. So we found transitive groups whose derangement graphs are a complete k-partite graph for these values of k. And here the degree of the group, the transitive groups in Sage, I think it's at most 37. And so the complete bipartite and the complete tripartite graphs are particularly interesting here. So what we found is the following. So there is only one transitive groups with k equal to 2, and the degree of this group is 2. So basically, the group is sim2, and its derangement graph is just like this, so the identity and the transposition 1, 2. And we only found 4 transitive groups whose derangement graphs were complete tripartite graphs. And I'll tell you why these ones are important later. And most importantly, so we couldn't find any other transitive groups whose derangement graphs were bipartite. And this is exactly what we proved. So if G is a transitive group, then the derangement graph is bipartite if and only if the degree of the group is at most 2. And this is the case that I described earlier. And when the degree of the group is at least 3, then we actually proved that a derangement graph must have a triangle. So it can never be bipartite. And a direct consequence of this theorem is the following. So when the degree of a transitive group is at least 3, then the intersection density is like this. So it's bounded from above by the degree divided by 3. And so our conjecture is the following. So this upper bound holds with equality if and only if the derangement graph is a complete tripartite graph. So that's why the transitive groups whose derangement graphs are complete tripartite are important. So these are some open questions. So the next conjecture says that basically for any k greater than 3, we can find a transitive group whose derangement graph is a complete k-partite graph. And this problem is just to find more transitive groups whose derangement graphs are complete tripartite graph. So in other words, more transitive groups where this equality hold. And maybe this is, I actually don't know if this is an easy question or a difficult question, but so here we have derangement graphs that are complete multipartite graphs with the same part. So in other words, they are they are actually strongly regular graphs. And if we look at Frobenius groups, so Karen proved on Monday that Frobenius groups have derangement graphs that are union of cliques of the same size. So they're also in primitive strongly regular graphs. So my next question is whether it is possible for a derangement graph of a transitive group to be a primitive strongly regular graph. And I suspect that the answer is no, but I don't have any proof. And so now let's talk about the chromatic number of derangement graphs. So if you are given a transitive group of degree n and this G, so I suppose that it is a subgroup of sim n here. So we can always partition the derangement graph of G as follows. So I take the point stabilizer. So one maps to 1, and I take the cosets of that. So basically what happens is that these guys are all co-cliques, and I can use n colors to color this derangement graph. So the next proposition is that if you have a transitive group of degree n, then the chromatic number is at most n, which is the degree. And so using this bound, we can prove that if G has the EKR property, then the chromatic number is exactly n. So my next question is basically asking whether if this is an if and only if statement. So does there exist a transitive group G whose chromatic number is equal to n, but G doesn't have the EKR property? And so now I'm gonna talk about some problems on the intersection density of transitive groups of certain degree. So so basically what we have is that if we take a transitive group G whose degree is a prime number, then using the click-co-click bound, we can actually easily prove that rho of G is equal to 1. So it has the EKR property. Li Song and Pantangyi proved that this also holds when we take a transitive group of degree pk, so a prime power. So rho of G is also equal to 1. And I worked on transitive groups whose degree is 2 times p, where p is an odd prime. So what I proved is that rho of G is a rational number between 1 and 2. And just recently, Dragan Marusic and his colleagues proved that what happens here is in fact just rho of G equal to 1 or rho of G equal to 2. And the next conjecture is the following. So if we take two distinct primes P and Q in a group of degree, a transitive group of degree PQ, then rho of G is equal to 1. So G has the EKR property. And I think we proved some part of this, but I think there is some groups that I'll mention later that we couldn't prove. Okay, so now I'm going to talk about the affine groups, the EKR property of the affine groups. So first of all, I'm going to recall what is an affine transformation. So we take a matrix in GL2 of Q and a vector in the FQ vector space FQ squared. So an affine transformation in this case is a map of this form. So this is our map, and the group AGL2Q is the set of all of these affine transformations, and it naturally has this this multiplication, which comes from the composition of two affine transformations. And the group structure is as follows. So it is the semi-direct product of FQ squared and GL2Q. So the FQ squared here represents the set of translation. So this is the case when of the linear transformations where the matrix A is equal to the identity matrix. And the GL2Q, of course, is when B is equal to 0. So AGL2Q act naturally on these vectors, and we can consider this as the points of the affine plane AG2Q. And this action is too transitive, so it has the EKR property. But we also have another action, which is the action on the lines of AG2Q. And this action has rank 3, and it is imprimitive. So since the rank is equal to 3, there is a unique system of imprimitivity, which is induced by the elements of PG1Q, so the lines that passes through 0. So the blocks, in fact, are just a set of parallel lines here. So if you take an element of PG1Q, then we just shift it by Q vectors, and we get some set of parallel lines here. So the degree of the group, in fact, is going to be Q times Q plus 1. So from now on, when I talk about AGL2Q, I mean this AGL2Q acting on the lines of AG2Q. So if we consider these blocks delta, so the system of imprimitivity that we saw earlier, then the stabilizer of the blocks is this subgroup, which consists of the affine transformations of this form where A is a scalar multiple of the identity. And so maybe it's worth to mention that this group is normal in this case. And we have a very special subgroup in the affine group that gives us a complete multipartite derangement graph. And it comes from a single cycle. So a single cycle is an element of order q squared minus 1 in GL2Q. And from this, the group GQS that we have here, we have a complete q plus 1 partite graph, and its intersection density is equal to q. And so this is the lattice of transitive subgroup of AGL2Q. So we have this branch. So this is a complete multipartite, and it doesn't have the AKR property. For this guy, I proved that it doesn't have the AKR property. Its chromatic number is equal to q plus 1. And we basically don't have tools to prove that the ones on the subgroups on this side do not have the AKR property, but that's what we conjecture. So the intersection density of AGL2Q is bounded by Q from above, and this follows from the no homomorphism lemma that Karen used on Monday. And for AGL 2.3 and 2.4, we were able to use SAGE to compute the intersection density. So they are all greater than 1. And we were able to prove that AGL2Q acting on the line doesn't have the AKR property. But we were able, in fact, to prove that there is an intersecting family of this size, but the upper bound that we have is just so terrible. I think it's not even worth to mention here. But my conjecture is the following. So basically, when Q is large, then the intersection density of AGL2Q acting on the line tends to 1 from above. And what we think happens is that if the maximum co-cliques of AGL2Q, of the derangement graph of AGL2Q, are in fact unions of cosets of the point stabilizer. So what I conjecture is that if F is an intersecting family of AGL2Q, then the size of F is the order of the point stabilizer multiplied by some function FQ, which is linear in Q. And the last one is the connection between AGL2Q and the group PGL2Q. So this is the stabilizer of the unique system of imprimitivity that we saw earlier. And this is a normal subgroup. So we tried to quotient AGL2Q with this, and what we got is PGL2Q in this case. And for ASL, we got PSL2Q. But the relation is just a bit strange because they are not like the one intersecting that we're thinking about. What we have is that if F is a two intersecting family of PGL2Q, then from this intersecting family, we can construct an intersecting family of AGL2Q. And the proof basically follows from the fact that this matrix here, AJ inverse AI, this has exactly 2 eigenvalues, and we can make this Q be intersecting. And my last problem is to find a sharp upper bound on the side of the max co-clique of AGL2Q acting on the line, and maybe find some other method other than the Hoffman bound, because the bound that one gave on AGL2Q and PG, the two intersecting for PGL is just terrible. And that's everything that I had today. Thank you for your attention.
Thank you, Biddy. Okay, do we have any questions?
I can ask a question to one of the conjectures. To the strongly regular graph one. Did you try that? Did you test that for a lot of small?
Yeah, yeah. Like I think I tried and I couldn't find any primitive strongly regular graph at all.
Okay, thank you.
Yeah.
Apologize if you've already addressed this and I just missed it, but is there any indication of how this intersection density parameter behaves with respect to sort of operations you might want to do to stick together groups or get sort of bounds, or taking some sort of interesting product or something?
Yeah, I think we really haven't tried that. The only thing that we tried was this one. So the intersection density in this case, they're equal.
Mm-hmm.
Yeah.
Yeah, I mean, I don't have any reason to expect that you get something nice in terms of it, but I don't know.
I'm not sure if I have a question, but could you go back to slide 27?
Okay.
I wrote it down for some reason. I can't remember why.
Yep.
Yeah, I think I was just wondering about this question. This is an open question, right?
Yeah, yeah, this is one.
Okay. It's an interesting one. Yeah, I don't really have a question here.
Okay.
Have you tried to figure out the chromatic number for AGL 2.4 or 2.5? 2.3 or 2.4?
I haven't. I think the problem is I use Sage. I don't know about other softwares, and as soon as it's more than 100 vertices, then I think it can't do it. Unless it has like a very special structure, I guess.
Maybe the PSL 2.4, 2.3 or something.
Yeah, maybe those ones. Maybe I should try those ones.
I think the Sage coloring routines are reasonably efficient. I mean, there might be better things out there, but you have to search for quite a while, and they won't be hugely better.
Okay.
Chromatic numbers hard.
Yeah.
For some reason, co-cliques you can do a lot easier.
I think
Yeah.
sometimes it helps to install Gurobi and tell Sage to use Gurobi as a solver because it's faster than the standard one, but I'm not sure about the
Yeah.
chromatic number out of my head.
Guess you could always compute the fractional chromatic number, but the question is how lousy of an approximation is that?
It's like the quote about you want to solve a computing problem, so you decide to use regular expressions, then you have two problems.
Maybe I can ask a question on the chromatic number. In some cases that are not related to groups, a nice way of figuring out the chromatic number is often to have a stability result for intersecting families, but I guess it's not really important here. Like you have a good idea what the best coloring is, and you know your colors are intersecting families. So if you have some kind of little bit of stability, it gets easier, but I'm not sure that's a reasonable question to ask.